Okay, so 1.3 forces in equilibrium. Explain forces in equilibrium. Forces are in equilibrium for an object when the forces acting on it produce zero resultant force. Okay, so we know when we want to get resultant force, we have a few forces. Okay, we have a few forces act on one object, and the single force, one single force that can give the same effect as a few forces combined together, that is what we call resultant force. But when there are many forces acting on the object, but the resultant force is zero, then we say that the forces are in equilibrium. That means they are all equal and balanced off each other. Okay. So what happens when forces are in equilibrium? From F equals ma, object with zero resultant force will have zero acceleration. That means when forces are in equilibrium, then the acceleration of the object will become zero. Object will be stationary or moving with constant velocity. That means if the object at the beginning is stationary, then it will continue to be stationary. If the object is moving, if the object originally is moving with constant velocity, then it will continue with its original velocity, continue to move in a straight line. Okay, so that is the motion of an object where forces that act on it are in equilibrium. Okay, let's look at an example. Okay, so we have vase. Okay, W is the weight of vase and flowers, and R is a normal reaction. Okay, here, calculate the resultant force acting on the vase and flower. So you see these two forces, weight and resultant force, these two are parallel. Okay, they are parallel to each other. So the way that we find resultant force for forces that are parallel is we just add them together. Okay, just add them together. Alright, so resultant force F equals to weight going downward, so we put negative 12, plus the normal reaction upwards, positive 12. So we get 0 Newton. Okay, we get 0 Newton. Alright, so you see 0 Newton. So forces acting on the vase and flowers are in equilibrium. Okay? Okay, so what is the effect of when the forces are in equilibrium on the flower and the vase? You see that the flower and the vase on the table, they are stationary. Okay, so that is the effect of forces in equilibrium on an object. Alright? Okay, continue. Okay, so this example is where the forces are parallel. Okay, now we want to see what happens if there are more than two forces. Okay, more than two forces and the forces are not parallel to each other. So for example, this one. So you look at this diagram, there's a lamp. Okay, and the lamp has a weight. So this weight is the result of gravitational force. Okay, weight is 4 Newton, so that means the gravitational force is pulling at the lamp with a force of 4 Newton. And then there is two strings. Okay, got two strings. One string pull to the left side 36.87 degree to the left, and the tension is 5 Newton. And then there's another string pulling straight to the right. Okay, straight to the right. That means 90 degree from the top. Okay, 90 degree. That means horizontally, horizontally. Okay, and the tension is 3 Newton. Alright, so we have 3 forces acting on this lamp. And just by looking at this lamp, we know that the forces are in equilibrium. How do we know that the forces that act on the lamp is equilibrium? The lamp is not moving. Okay, the lamp is stationary right now. So the lamp is stationary, that means the resultant force is 0. Resultant force is 0, that means the forces are in equilibrium. Okay, the forces are all balanced. The 5 Newton, 3 Newton, and the 4 Newton all balanced with each other. Okay? Alright. So, this part we want to sketch a triangle of forces in equilibrium. Triangle of forces are a triangle where the side of the triangle can represent the 3 forces that act on a single object. And the 3 forces are in equilibrium. Okay? Okay, so we look at this A. Based on concept of scale diagram, parallelogram method. So remember we learned this in topic 1.1, parallelogram method. Calculate the resultant force F of force T and force P. So that means now what we want to do is we don't look at this 4 Newton. We just look at this force T and force P, these 2 forces. Okay, so these 2 forces acting on the lamp is over here. So 5 Newton and 3 Newton act on the lamp, and the combine of 5 Newton and 3 Newton will produce a resultant force that is upward, directly going up. Okay, like this. This is the resultant force. This is the resultant force from resultant force of 5 Newton and 3 Newton. Why is it that we know that the resultant force of 5 Newton and 3 Newton is directly going upwards? Because this resultant force is there to balance off. The resultant force must balance or must go against the weight, which is 4 Newton. Okay, this one and this one, they must be directly opposite each other. Then this one, the resultant force will be able to cancel off this weight that is 4 Newton. Then the forces will be in equilibrium. Okay, so now we want to calculate this 5 Newton and 3 Newton, see whether really the resultant force is the same as 4 Newton or not. Okay, so from these 2 forces in this direction, so we can draw a parallelogram. So this is the same length as T equal 5 Newton. So this length represents 5 Newton, and this length, this line here is the same length as this one. So this one also represents 3 Newton. Okay? Alright. So from this parallelogram, we can obtain a triangle. Okay, a right angle triangle. Okay, we can obtain a right angle triangle. So you can get the right angle triangle from here or from here. Okay, you have 2 choices, either here or here. For me, I prefer this one. Okay, I prefer here. Alright. Wait. Okay, I think the easier one is Yeah. Okay, the easier triangle to get is this one. Okay, this triangle is easier. Why this triangle is easier to use? Because there is already an angle inside the triangle. You see or not? This angle 36.87 degree is already inside here. 36.87 degree is already inside here. This is 90 degree. This is 3 Newton. This is 5 Newton. So this is the resultant force. Okay, this is the resultant force. This is 5 Newton, this is 3 Newton. Alright? Okay. If we take this triangle, you see inside this triangle there is only the 90 degree. So if you want to calculate the length of this side, it will be a little bit more difficult. Unless okay. So you want to calculate this side, so you need angle inside here. Okay, you need angle inside here. So you have to see this 36.87. Where is this 36.87 inside this triangle? So you can see that this 36.87 is here, over here. This angle is the same as this angle. Okay, these two is the same. 36.87. Here also 36.87. Okay, but of course, you can go take the extra step to go and find out where is the angle inside this triangle. But there is a chance that we may make mistake when we identify the position of the angle. For example, many students make mistake. They think that okay, here is 36.87, so here also 36.87. So this is a common mistake that is made by student. Here 36.87 or here also 36.87. Okay, that means the student do not think logically, just follow the feeling. Just follow feeling. This one 36.87. Or this one also feel like also 36.87. So 36.87. So make a mistake. Okay. So so better to take this triangle where the angle is already inside. If the angle already inside, also you won't make mistake putting the angle at the wrong position. Okay, so now we have a triangle, right angle triangle. So we can use Pythagoras Theorem to calculate this length is, what is the length of, what is this length? Either you want to use Pythagoras Theorem also can, or you want to use trigonometry also can. Okay, you want to use trigo also can, you want to use Pythagoras Theorem also can. Okay, so for example, I use, okay, since we have the angle, so we use trigonometry lah. Okay, so I use cos lah, okay, because this f is beside the 36.87, so I use cos. So cos 36.87 degree equals to big friend, move down here. Okay, so equal to F over 5 Newton. So F is equal to, alright, so after we calculate, we get that the force is, the resultant force is 4 Newton. Okay, resultant force is 4 Newton. And you see that it is equal with the weight. Okay, equal with the weight. Okay, compare resultant force F with weight of length. Resultant force F equal to weight. Alright, equal to the weight. Okay, so resultant force, this resultant force, okay, I want to stress that this resultant force is the resultant force of these two forces, T and P. Okay, now this resultant force acting on the length is the resultant force from all three forces acting on the lamp. So the resultant force of all three forces acting on the lamp is 0. Okay, because this 4 Newton going upward can represent these two right now. So that means if you don't have these two, you can put this 4 Newton going upward to represent these two. So that means what you have is, this one is the lamp. So this is the resultant force of T and P, which is 4 Newton, and the weight is 4 Newton. Okay, you see that? So it becomes like this. So if it becomes like this, so that means 4 Newton up, 4 Newton down, so the resultant force acting on the lamp is 0. So the forces acting on the lamp are in equilibrium. Okay? Okay, let's continue. Alright, so based on the result from A, resultant force of P and W is P and W. You see, the resultant force of T and P is same as 4 Newton, okay, going upwards. Okay, so if like this, then the forces are in equilibrium and balanced, so the lamp not going to move. So that means from here, from what we see here, how about the resultant force of P and W? How much do you think is the resultant force of P and W? If we count the resultant force of P and W, how much do you think that you can get? Okay, so P and W combine, the resultant force, you will get 5 Newton. And this 5 Newton is directly opposite this T, this 5 Newton. So this 5 Newton and this 5 Newton, they balance off each other. So the forces will be equilibrium. Okay, the forces, the resultant force will be 0, so the forces are in equilibrium. So same concept also, this T and W combined, we will be able to get 3 Newton. Okay, we will be able to get 3 Newton. So this 3 Newton will balance off with this 3 Newton. So resultant force is 0. So you see, when forces are in equilibrium, when forces that act on an object is equilibrium, I don't care how many forces there are acting on the object, the resultant force from any direction will be the same, which is 0. Okay, the resultant force will definitely be 0. Okay, so resultant force of P and W will be 5 Newton, and then T and W will be 3 Newton. Alright, so resultant force acting on the lamp is 0. Okay, continue. So based on A, triangle of forces can be obtained. So from this triangle, okay, this same triangle just now, this parallelogram from here. Okay, this parallelogram. Okay, this one is 5 Newton. This one is 3 Newton. So this is 4 Newton. This is the resultant force of these two. Okay, so based on A, triangle of forces can be obtained. So here, okay, we obtain a triangle. Okay, so this is a triangle. Okay, this is a triangle, right? We get a triangle from here. Alright, so we can substitute resultant force F with weight of length. That means this force, this one, okay, this force F, the resultant force of 3 Newton and 5 Newton, we can substitute with weight. Weight is going downward. Is 4 Newton. So why is it that we can substitute this with weight? The reason is because they are equal in magnitude. If they are equal in magnitude, and remember the concept of the parallelogram is that the length of the line represents the magnitude of the force. Okay, for example, 1 centimeter represents 1 Newton. So if 4 Newton, then the length of the line is 4 centimeter. So because the resultant force of 3 Newton and 5 Newton is 4 Newton, so we say that, let's say that this length is 4 centimeter. And the weight is also 4 Newton. So that means the length of the line that can represent weight is also 4 Newton. So we can substitute, we can replace this resultant force with the weight of the length. Then we get a triangle. Okay, this is 3 Newton. This is 5 Newton. Degree, so this is 36.87 degree. And this line replaced with weight, so weight is going downward. 4 Newton. Okay? Let's see or not. So you see, now this triangle, okay, now this triangle is a triangle of forces. Okay, this is a triangle of forces in equilibrium. Okay, a triangle of forces in equilibrium. Let's see or not. Because you see, this triangle represents the relationship between 3 forces. 3 Newton, 5 Newton, 4 Newton. All of these 3 forces are actual forces. Okay, they are actual force that are actually acting on the land. Okay, the 3 Newton is the tension of the string P. The 5 Newton is the tension of the string T, and 4 Newton is the weight, which is gravitational force. So all of these forces are actual forces that are acting on the land. And the relationship between all these 3 forces can be represented with triangle of forces. And how do we see that this triangle of forces, the forces in this triangle are in equilibrium? We see that the direction of the forces, you see the direction, this one going to the right, this one going down, and then this one going up like this. So you see that these 3 forces, the direction, they are in one cycle like that, okay, like in one cycle, going in one round like that, okay, going in circle. So if you see that the triangle, if you see there's a triangle where the direction of the forces are all going in one cycle like that, then that means that the forces are in equilibrium. If the forces are not in equilibrium, for example, let's say this one, okay, let's say this one. You see, this one 5 Newton going up, this one 3 Newton going to the right, and then there's 4 Newton going up. So that means that this is not a cycle. So that means the forces are not in equilibrium. This is of course if we do not have a force going down. Okay, if we do not have a force going down, then these forces will not be in equilibrium. Okay, you get the idea. But of course, this 4 Newton is actually resultant force from the 3 Newton and 5 Newton. Okay, they are not actual force. This 4 Newton is not actual force that act on the object. This 4 Newton come from this 3 and 5 Newton also. So actually only got 2 force here. Okay, this triangle, sorry, this is not a good example. Okay, I give you another example. Okay, I give you another example. So let's say okay, let's say okay, same thing, length. Okay, we have one force here, 5 Newton, another force here, 3 Newton, and another force here, pulling upwards, 4 Newton. These three are all actual forces. Okay, let's say they are actual forces, they are acting on the length. Okay, for actual forces, they are actually acting on the length. So, the triangle of these three forces, it will look like this. Okay, this one 5 Newton, this one 4 Newton, this one is 3 Newton. So you see, the three forces, they are not in one cycle. Okay, they are not in one cycle. Let's say they don't have weight. Okay, then no weight. Okay, let's say no weight. Let's say no gravity. Okay, let's say this is in space, no gravity, so no weight. And then we have three forces that pull on this length. So you see the triangle of forces, it will look like this. Okay, the triangle of forces will look like this. So if this is the case, then it will mean that the forces are not in equilibrium. If the forces are not in equilibrium, that means the resultant force is not equal to 0. If resultant force not equal to 0, what will happen to the object? Object will accelerate. Okay, the object will experience acceleration. Get the idea? Because F equals to ma. If this resultant force is not 0, a resultant force acting on this mass, then this mass will have this acceleration. So if this F is not 0, then the mass will have acceleration. If the force is this resultant force is 0, then this mass, the acceleration will be 0. Okay, the acceleration will be 0. Okay, get the idea. Okay, so I hope you can be able to differentiate triangle of forces that show forces in equilibrium and triangle of forces that show forces that are not in equilibrium. Okay? Okay, now, so this is the basic concept, of obtaining a triangle of forces in equilibrium. That means we follow the concept. Get a parallelogram first. Okay? From the parallelogram, get triangle. From the triangle, we get the triangle of forces. Okay, step by step, follow the concept. However, there is a shortcut lah. Okay, there is a shortcut. The shortcut is this one, E. A simple way to obtain a triangle of forces for forces in equilibrium is by moving the lines that represent the forces to form a triangle without changing the direction of the forces. That means like this. Okay, that means like this. So, okay, so there is a length, and then we have a force here, and then there is another force here, and then there is another force here. Okay, I purposely draw the line not to touch the length so that later I can move the line easier for me to move the line. Okay, but if you draw, let's say if you draw the what we call okay, here I draw the diagram. The line that represents the forces do not touch. This is so that later I can move the line easier for me to move the line later. But when you draw actual diagram, okay, if you draw diagram, okay, that show the forces that act on the object, okay, this kind of diagram is what we call a free body diagram. Okay. So when you draw free body diagram, make sure that the line that represent the forces must touch the object. We must touch. Okay, but here I purposely draw it not to touch so that I can cut the line and move it. Okay, easier for me to move. Okay, so now, so this is 3 Newton, this is 5 Newton, this is 4 Newton. Okay, so you see, we want to do the shortcut method to get the triangle of forces. Okay, so one more time, a simple way to obtain a triangle of forces is by moving the line that represent the forces to form a triangle without changing the direction of the forces. Okay, that means the direction of the line cannot change. Okay, so for example, we have these three forces that are acting on the length. Okay, so we can move these three lines freely. Okay, let's say I move this one. Move this one here. Okay, you see I can move it anywhere. I can move here, I can move here, I can move here, here, I don't care. Okay, I can move anywhere. I can move the line anywhere, but the direction still going to the right. You see or not? The direction still going to the right. The direction doesn't change. Okay, and then this one, I can move. I move here. For example, I move here. Okay, you see or not? I can move. I put here. I want. If I can put here also can. I put here also can. I put here also can. Anywhere also can. This one also can. This one also can. Anywhere also can. Okay, let's say I put here lah. And then this one, I move this one. Put here. Okay, I move this one. Put here. So you see, become a triangle. This one is the last line, so I cannot simply put anywhere lah, because I need to put at the place where it will form a triangle. You see or not? So if I put here, then it become a triangle. See or not? Here I join. So become a triangle of forces. So very simple. So you see this triangle is the same as what we get from parallelogram. Okay, this is the same as what we get from the parallelogram. So you see this method is very easy lah, okay, very simple. But we must not forget the actual concept. That means what we do here, building this triangle of forces is based on what concept? Okay, based on what? We must understand what does it based on. Okay? Okay, now, so let's try example. Okay, let's try this example. Let's look at the example. Okay, so we have an inclined plane and we have three forces acting on this box. There's weight, this is the friction, and then this is the normal reaction. Okay, normal reaction. So we want to build triangle of forces that represent these three forces. Okay, so we just use this simple way lah. Okay, use a simple way, the shortcut method. Alright, so let's say I draw the weight lah. This one, the weight I put here. Okay, I put the weight I put here. And let's say, okay, the next one that I draw is this one, the normal reaction. So normal reaction is, okay, let's say I put here, okay, I put the normal reaction here. Okay, the direction must be the same, the direction is still the same. Okay, the only thing that changed is the position. Okay, so this one is W, this one is R. So you see this, the normal reaction is still going in this direction. This one going in this direction, this one going in this direction. So the direction must still be the same. After that, we want to put this friction. So friction, the only place is here, okay, in order to form the triangle. Okay. So this is the friction. Okay. And now we have a triangle. Another thing that is very important inside the triangle is the angle. Okay, we must make sure we label the angle inside. Alright, so first is you see this normal reaction and the friction. This normal reaction and friction, they are 90 degree right now. Okay, so that means this one and this one, friction, and the reaction, this one is 90 degree. Next is this angle, this theta. Where is this theta? Okay, where is this angle theta? Alright, so from here we can see that the angle between this normal reaction and this weight here, this angle is actually theta. Okay, this angle is actually theta. So how is it that we can get that the angle is here? This angle here is theta because okay, this is 90 degree. So that means this is 90 minus theta. This is 90 minus theta. Okay, so the weight is here going downwards. Okay, this is weight. Okay, this is R. Normal reaction, this is weight. So if this side is 90 minus theta, so and this is 90. Okay, this is 90, and this is 90 also. So 90, see this one here is 90. So that means this angle, okay, this angle is 90 minus theta. So that means you get theta. So that means this angle is theta. Okay, so this one is theta. Alright, so so that means where is this theta actually? Okay, where is this theta actually? So we can deduce that, okay, so this is, okay, so this one is theta, this side is theta. The reason is because this is theta, this is 90, so this is 90 minus theta. Okay, so okay, I think I move this weight and this line and this weight I move. I draw this weight here. Okay. Okay, so maybe you can see more clearly like this. Okay, so this is 90. Okay, this is 90. So this is 90 minus theta. And this side here, this is also theta. Because this one is 90, this side is 90 also. Okay, this side is 90. This side is 90 minus theta. So that means this side is 90 minus 90 minus theta. So we get theta in here. Okay, and this triangle we can get by moving. Okay, let's say this weight is over here. Okay, let's say the weight is over here. Okay, this is weight. And this friction we put over here. So this is the triangle of forces lah. Same this is the triangle of forces here. So this angle theta, this side is also theta. Okay, because this line and this line they cross each other, so the angle here and the angle here is the same. So that means here, over here, it will be the theta. Okay, alright, so with this, the triangle of forces is complete. Okay, like this, the triangle of forces complete. Okay, when we draw triangle of forces, we must label the direction of the forces, label the forces, and label the angle inside the triangle of forces. Okay, if the triangle of forces is right angle triangle, so you must label where is the 90 degree and together with another angle. The third angle you don't label also never mind. That means this one you don't label also never mind. But minimum you must have two lah. Okay. But if the triangle is not right angle triangle, that means triangle that do not have 90 degree, then you only need to label one of the angle. Okay, only need to label one of the angle inside the triangle. Alright. Basically, if the question will give you any angle, then you label it inside the triangle. Okay, but of course you must label at the correct position. Okay, label the angle at the correct place. If the question will give you all of the angle of the forces, they will give you all the angle, then you need to label all of them inside the triangle. Alright. Okay, let's look at this number 2. Okay, so like what we discussed just now, to draw the triangle of forces is actually very simple. We just move the these three forces, these three lines that represent the three forces, okay, to form the triangle of forces. So let's say, okay, so we have, okay, so let's say we have three lines, okay, this is the weight. Okay, this is tension, okay, we have tension, and another line, this one is, okay, so the angle here is alpha, the angle here is alpha. Okay, angle here is alpha. Alright, so we move these three lines, okay, move these three lines. So we can move this one. Okay, we can put this one, okay, let's say I put this one over here. Okay, and then I can move this one over here, and this one over here. Okay, so I just make it longer, and we can get the triangle of forces. So you see this one, this is a triangle of forces that represent these three forces, okay, relationship between these three forces. Okay, so this angle is here lah. Okay, this alpha is here. Okay, this one is alpha, this one is alpha. Okay, like that. So that means the angle between the two tension, T and T, the angle between them is 2 alpha. Okay, the angle between them is 2 alpha. Okay, Anna. Okay, I repeat. So you see this triangle, the direction is in one cycle. Okay, this one going up, going down, going up. Okay, one cycle. So when it's in the cycle, it shows that the forces are in equilibrium. Okay, so this number 3. Alright, so this R is the water resistance. Okay, we can put the water resistance here. Okay, R. And this one tension, going up an angle theta. Okay, you can put like this here. And what I say, we can move the line that represent the tension anywhere, but we do not change the direction. I make sure that this direction is still the same as this one. This one is still going up. This other way up. This. Okay, so this is theta. Why this is theta? Like what I say, the direction of the line is still the same. So if this T is in the same direction as this one, so this angle must be theta. Okay, same. And then the next one, this one, we put here lah. Okay, here. So what is the angle? Where is this angle? So this angle is here. Okay, this angle is here. This one is also theta. Okay, why? Because you see this is R. Okay, and this is T. So this is R, this is T. So this angle theta, that means here is also theta. Okay, get the idea. Yeah. So another way to see that okay, this angle and this angle is the same is that this is T and this one also T. If this is T, this one also T, that means the force. That means these two forces are the same magnitude, same size. If it is the same magnitude, same size, that means that the length of the line is also the same. If the length of the line is the same, that means this triangle is isosceles triangle. Right. Is it isosceles triangle or equilateral triangle? Okay. I'm not sure about the name I forgot. Okay, but this means that this triangle has two sides that are the same length. So these two sides have the same length. So that means this angle and this angle is the same. Okay. Right. So solve problem involving forces in equilibrium. So let's look at example. Okay. Figure show a stationary lamp hanging from two strings. The tension T is 8 Newton. The string is inclined at an angle of 60 degrees above the horizontal, as shown in the diagram. We calculate the magnitude of the tension, okay, and then the weight of the lamp W. So that means we need to calculate this one is how much and this one is how much. Okay, now you see here, here got say method 1, method 2, no need lah. Okay, no need. This one, method 1, no need. Okay, just cancel off this method 1. Because this method 1 is, although can use, but too troublesome. Okay, too troublesome. So we just learn to do with two methods. Okay, the first one is scale diagram. Okay. Okay, method 1 is scale drawing. Okay, scale drawing of the triangle of forces. Alright, so if we want to draw scale diagram, that means we need to have a scale. So let's say that it is 1 Newton, let's say 1 centimeter to 1 Newton. Okay, 1 centimeter to 1 Newton. And so we can draw. Okay, we draw a rough one first. We draw a rough one first. Okay, so this one weight going down, T to the right, and this T going upward left. Right? So the rough one, the triangle that we can get is like this. This one weight down. And then P here, and then the T here. Okay, so this is 60 degrees. This is the weight. This is the T equals to 8 Newton. This is P. Alright, so we draw. This is 90. So first, this T lah. Okay, this T 8 Newton. So we draw a line. About 8 centimeter long, roughly lah. We measure with ruler. Okay, 8 centimeter is here and here. Okay, so this is 8 centimeter. Okay, 8 Newton, and then we use protractor to measure 60 degree. Okay, you measure this one 60 degree, you draw a line. Okay, but this one P, we don't know what is the length right now. Okay, we don't know what is the length, so you just draw a line that longer a bit lah. Okay, and then after that you use protractor, you measure 90 degree. Okay, you see this one is 90, this one is 60, so that means this side must be 30 right now. This side must be 30. So here you measure 30 degree and you draw a line down. Okay, you measure 30 degree and then you draw a line. Okay, use protractor, measure 30 degree and then draw one line until you join here. And then after that you take your protractor and you measure here. See whether you can get 90 or not. If you can get 90, then that means it's correct lah. Okay, here 60, 30, this one 90. Okay, so after that, that means now you get your triangle of forces already. So this length of this line will represent the weight, and then the length of this line represent the tension P. So just by measuring the length of W and the length of P here, then you can get the answer for A and D lah. Okay, how much is the tension P, how much is the weight of the length. Okay, get the idea. Okay, but this is a scale diagram lah. Okay, this is scale diagram. So next we want to do calculation. Okay, because the question asks us to calculate, so the best way is actually to calculate lah. But I want to show you the scale diagram method to prove the concept, so that later we can compare the result, that means the answer from the scale diagram and the answer from the calculation. We will be able to see that they are actually very close, or you can get exactly the same. Okay? Okay, now, so for calculation, okay, for calculation, must based on the triangle of forces also lah. That means the first step is you still need to get the triangle of forces. So after you get the triangle of forces, so you get the right angle triangle. And because this is a right angle triangle, you have the angle 60 degree, you have the key, this one is 8 Newton, so that means you can calculate by using trigonometry lah. Okay, you can calculate tension P by using cos. Okay, cos 60 degree equals to P over 8. So P is equal to So you get 4 Newton. Okay, so P is 4 Newton. And then after that, this W, you can use sine. Okay, so sine 60 equals to W over 8. So W equals to 6.928 Newton. Okay, so this is the answer from calculation. All right. But again, I must stress that the calculation is still based on the triangle of forces. That means the first step is you must get the triangle of forces. Okay. Then after that, you can draw a scale diagram or you can do calculation straight away. Alright. Okay, let's look at number 2. Okay, figure show a box of weight 50 Newton stationary on an inclined plane. Okay, A. Draw a free body diagram of the box showing the weight of the box. Weight of the box W, normal reaction R, and the frictional force Fr. Okay, so free body diagram is the diagram that shows the forces, all of the forces that act on an object. Okay, so first is the weight of the box. So the weight of the box you can put here. Okay, this is the weight. And then normal reaction. And then frictional force. Okay, so this is the free body diagram of the 3 forces that act on this box. Right? Okay, so B. By drawing a scale diagram of forces drawing a scale triangle of forces diagram, determine the magnitude of the normal reaction R and the frictional force Fr. Okay, so this question specifically wants us to draw a scale triangle of forces diagram. That means we need to draw scale diagram. Okay, so before we draw the actual scale diagram, we draw a rough one first. Okay, we draw a rough one. Okay, so this is weight. Okay, this is weight. And this is the friction. And this is the normal reaction. Okay, so normal reaction and the friction is 90° perpendicular. And this is the weight. Okay, so where is the 40°? Okay, where is the 40°? From here we can see, okay, if this is the weight here. Okay, this is the friction, this is the weight. So this is 40 here. Then that means this is 60. Now this is 90°. So this is 60. So this is 40 lah. This is 90. Okay, so this is the triangle of forces here. Okay, so this is 40. Alright, this is 60. Okay, So we want to determine the magnitude of normal reaction R and frictional force Fr. Alright. So it says that the weight is 50 Newton. So that means you need to measure. Okay, so we need to determine a scale first. Determine a scale. So we can take 1 centimeter to 1 centimeter. Okay, if you want because the weight is 50 Newton, so we want it to be we want our diagram to be bigger a bit, so we put 5 okay, 5 Newton. 1 centimeter represent 5 Newton. So the 50 Newton length will be 10 centimeter. Okay? Okay, so we can draw this one. Let me make sure it's about 50 centimeter. Okay, sorry, 10 centimeter. Okay, so here to here. Alright, so this is the weight, okay, 10 centimeter. And then okay, need to use protractor and measure 60 degree, but unfortunately right now I do not have protractor. Okay. Okay, so I draw roughly lah. Okay, I roughly draw, so you can so you have protractor, you draw the proper one. Okay, so let's say 60 roughly here lah. Okay, roughly. Okay, roughly here. So draw a long line. Okay. So this is the friction. And then draw the normal reaction from here. Okay, this one you measure 60 degree. This one you measure, use protractor and measure 40 degree. Okay, use protractor, measure 40 degree, and then draw over here until here. Okay, so this is 90, this is 40 lah. So make sure you check using protractor, make sure that this is 40, this is 60, this is 90. Okay, in your diagram, make sure that this is 40, 60, 90. Alright, this is the normal reaction. Okay, so after you draw already, how is it that we know this friction is how much and the reaction is how much? We measure, take ruler, put here, and we see this normal, this friction is how much? How long is this friction? Okay. So how many centimeter times 5 Newton? Then you get how many Newton lah? Okay. And then after that you put ruler, you measure this length is how much? Equals to how many cm times 5 Newton equals to how many Newton? But when you write the how many centimeter here, you just write the number lah, don't write the centimeter. Okay, just write the number. For example, if this is like 8, okay, for example let's say if this is 8 centimeter, then you just write 8 lah. Don't write like 8 centimeter. Okay, just write 8. 8 times 5 how many Newton? This one how many centimeter? Don't write centimeter, just write the number times 5 equals to how many Newton? Okay, so this is scale diagram. This scale diagram. Alright, so after that, C, by resolving the weight of the box into a component parallel to the inclined plane and a component perpendicular to the inclined plane, determine the magnitude of normal reaction and frictional force. Okay, so that means this part C, they want us to do another method. That means use resolution of forces. Resolution of forces to find the normal reaction and the frictional force. Okay, this is B and C. Okay, we want to do resolution of forces. Okay, so this is the inclined plane. This the box is here. Okay, this angle, this is 40. And then this is the weight downward. Again, the weight, right? Okay, this is the friction. This is the normal reaction. Okay, so we want to resolve this weight into the horizontal component and vertical component. Horizontal component is a component that is parallel with the inclined plane. So I use, let's say, this green color. Okay, so this is the component that is parallel with the inclined plane. This is the component that is perpendicular with the inclined plane. Okay, I use Fy, this one Fx. Okay, the angle over here is 40 degrees. Okay, so you see here, we can get parallelogram now. Okay, so from parallelogram, we can get a right angle triangle. Let's say I take this right angle triangle. Okay. So I get this right angle triangle. This is 40. And this is x. This is weight. Alright, so the angle. Okay, so this weight is 50 Newton. Okay, so this weight is 50 Newton. Okay, so we can calculate this Fx and Fy. So this Fx is opposite to the 40, so we can use sine. Sine 40 equals to Fx over 50. So Fx equals to, okay, we get 32.14 Newton. Okay, and then for the Fy, we use cos because it's adjacent. Cos 40 Fy over 50. Okay, so Fy is 32.14 Newton. Okay? Okay, mistake. Press wrongly. So this is 38.3 okay? 38.3 Newton. Alright? Okay, so after we get this Fx and Fy, Okay, you see, it says here, by resolving the weight into component parallel to the inclined plane and component perpendicular to the inclined plane, determine magnitude of the normal reaction and frictional force. Okay, so we look at the question. It says, figure show box of weight 15 newtons stationary. If stationary, that means it's not moving. That means what? That means this friction and this Fx is equal to each other. This Fy and this reaction is equal to each other. So you see all the forces are in equilibrium. Okay, these two balance, these two balance. So all the forces are in equilibrium. Okay, you see, this Fx and Fy both are component of W. That means Fx and Fy can replace W. Okay, so if Fr equal with Fx, R equal with Fy, so that means all the forces are in equilibrium. Okay, all right. So we know that it is in equilibrium because the question already say that it is stationary, right? So we know that it's stationary, then we know that this friction equals to Fx. Reaction equals to Fy. So Fx we already found out, Fy also found out. So we can answer the question. We say that Fr equals to Fx equals to 32.14 Newton. And the R equals to Fy equals to 38.3 Newton. Okay, done.